So, from today we will discuss some string matching algorithms. So, let us describe the problem. Suppose you are given a string T of say length n, and so we call it a text string, and another string P we will call pattern string as B1, B2, Bn. Our goal is, and usually n is greater than or equal to m, and our problem is to see if there exists some position in this string T from where contiguous m symbols match these symbols. So, we want to know, does there exist I such that ai I plus 1 I plus m minus 1 is same as Bn, and if possible we would like to compute that I. Now, indeed, of course, if m is greater than n, there is no solution to this. The trivial solution to this problem is to start matching the pattern string symbol by symbol starting from the first position. If we succeed all the way up to an, then we have a solution. Else, we repeat the entire process starting at A2, and we continue to do that. If at all we ever succeed, then we do have an affirmative answer to this. Else, there is no way there is any string, substring of T which matches with P. So, let us write down the simple or so called brute force algorithm. So, we begin with I at 1, and then we are going to, so let us say we will have some flags later on. So, while not of flag, this flag will indicate that we have succeeded in finding such a string. So, initially flag is false, or and we haven't gone too far on this string such that if we reach a point beyond which there are not enough symbols left, then there is no point in matching. So, the last point where we will try to match will be n minus m plus 1. So, I is less than or equal to n minus m plus 1. While both these conditions hold, then there is a need for checking for such a substring. So, what we will do is we will begin with j equal to 1 and try to match ai with b1, that is bj, ai plus 1 with b2 and so on. So, we will say while a I plus j minus 1 is bj, and j is still not m, then we set j equal to j plus 1. We have succeeded in matching up to j value, and we are extending it to j plus 1. Yes, we have to match up to the mth symbol. When we come out of this, and if j value is m plus 1, then we know that we have matched all the m symbols. So, when we come out, if j is m plus 1, then we set our flag to true, else we have to start a fresh search starting from the next value, namely I plus 1. So, we will set our I to be I plus 1. This loop will terminate eventually either with a success, that is flag would be true, or I would have exceeded this last limit. So, we will say if flag is true, okay, then return I. I is the position from where we found the match, else now notice that it is possible that the success was at the very end of the text string, but if the flag is not true, that means we have not found the matching substring. So, we will simply state that a failure. This algorithm, in the worst case, suppose there is no such string, there is no place in the text string where we find these symbols together, then we are going to match these m symbols here starting from position 1. That will account for order m work, then again we will match m symbols, and again we will match m symbols. So, the total cost, the time complexity is going to be order m times the total number of symbols starting which we are going to do this search, which is n minus m plus 1. So, it will be n minus m plus 1. In general, m is significantly larger than m, and this is going to be n times m. Now, what we will see next is that in this process we have done lot of duplication of work, and we will discuss a way to avoid that and improve the performance of the algorithm. Now, this improved algorithm is due to Knuth, Morris and Pratt, and the algorithm is named after them. Let us try to analyze the situation when we find a failure. Let us suppose we have our text string Let us suppose at some stage we started matching B1 with this and proceeded up to this point. So, first R symbols of the R is less than M, first R symbols of the pattern string do match with these successive symbols of the text string. And here we find that there is a mismatch. We find that this is not proceeding any further. At this stage, we will begin matching with the next symbol with B1 and proceed again, trying to find whether this matches with B1, the next one matches with B2 and so on, whether AJ matches with BR minus 1, and then we will see whether the next symbol matches with BR. This is what we will be doing. Now, notice that these symbols are precisely these, because we have already done the matching. So, the question is B1 equal to B2? Because the next symbol, which is Bj minus R plus 2, is same as B2. So, we would be asking, is B1 equal to B2? Is B2 equal to B3, and so on. Now, clearly this test, of course, after that we will worry about the next symbol, but up to this point, whatever we want to know is an information which is exclusively available by analyzing the pattern string alone. We do not really need to know what this is. We can very well ask the same question just looking at the pattern string and say, if is B2 equal to B1, is B3 equal to B2, and so on, BR equal to BR minus 1. And suppose we find that that is not working, then I will go to the next symbol and I will ask whether B1 is equal to B3 and B2 is equal to B4, and so on. I will continue to search, and maybe I will find eventually some place where certain number of symbols here are same as the same number of symbols at the start of the B string. If we do not find any of these, then of course we will have to move on and start searching from here. This suggests that we could do certain initial processing before we even begin with searching the text string. And this suggests the following computation that is required. What this says is that here is B1, B2, B3, say Bj, and I would like to know what is the earliest symbol, say Bk, such that this string is same as this string. Isn't that what we want? So, we would like to stay to our left as far as possible and locate a string, that is to say, as long as a string as possible, which is equal to the last symbols as well as the first so many symbols of the pattern. So, here let us use a term which is called an initial substring . An initial substring of a given string, initial string of some string x. X is, let us say, x1 through xt. Any contiguous string, that is to say x1, x2, x3 up to xi. Any contiguous string from 1 to I is called an initial substring of x. Similarly, a terminal substring of x would be would be a string starting from any xj to xt. This contiguous substring, this will be called a terminal substring of x. Now, what is our objective right now? We would like to find a longest possible initial substring of B1 through Bj, which is also a terminal substring of B1 through Bj. Okay. So, question is, for any j, what is the longest proper substring? We do not want the whole thing, which is obviously the case. That is not of our interest. We want a string shorter than j. What is the longest proper substring of B1 through Bj, which is an initial as well as a terminal substring of this. So, we will define a simple function f. This would be k if B1 through Bk is the largest proper substring, initial and terminal. So, k has to be strictly less than j. If you find nothing, if there is no string which is both initial and terminal, then we will output 0. So, what we will do is, we will first describe an efficient method to compute this, and then we will go on to devise an algorithm based on this information. Okay. So, now let us devise an algorithm to compute the value of the function we have just defined. Let us call this f. Okay. We just call it algorithm f, and this is of course a function of the pattern P, which is B1 through Bm. Function f the proper substring of a single symbol string is empty string. So, there is nothing there. We are going to build from lower to higher argument of f. So, let us suppose, so let us first put this in a loop for j equal to 1 to m minus 1. We have the value of fj, and in each pass we want to compute the value of fj plus 1. Now, it is clear that if let us just keep the picture here, that we have our B1 through Bj, and this is Bj plus 1. We want a longest substring which is initial and terminal in this. Now, what we have is the longest initial string which is also terminal of this part. Let us say that string is this big, it goes from B1 to Bk. That means f of j is k. Now, if it so happens that Bk plus 1 is same as Bj plus 1, that is, say, if f we will say I equal to f of j. Now, if b of I plus 1 is equal to b j plus 1, let us just call it I. So, if bi plus 1, the next symbol, is same as this, then f j plus 1 will be I plus 1. The symbol next to this. The f is indicating the index. So, if you are lucky that the very next symbol matches with the next symbol here, then the longest string, which is initial and terminal for the bigger string b, is actually one more than the f of j. But what if it is not? If this is not the case, then there will be a smaller string, hopefully. Whatever that string is, say up to this point, let us suppose this is Bk. Such that B1 through Bk plus 1 is also a terminal string. Let us suppose that is the case. Alright. So, here we find Bk plus 1 through some B1. This is a terminal string as well as Bk plus 1. B1 through Bk plus 1 is also the initial string. Now, in that case, B1 through Bk is also an initial and terminal string of B1 through Bj. If B1 through Bk plus 1 is initial and terminal string of B1 through Bj plus 1, then B1 through Bk is initial and terminal substring of B1 through Bj. Now, let us go back and look at B1 through Bi. Okay. So, we know that B1 through Bj has this string B1 through Bk, and it is also matching here B1 through Bk. But we have already a longer string B1 through Bi, which is initial and terminal in Bj, because my I is equal to f of j. I is f of j. So, there is this up to Bi, this string, and over here it is B1 through Bi. What we notice is that this B1 through Bk is also initial and terminal substring of B1 through Bi. Notice that this is B1 through Bi and B1 through Bk is an initial substring, and this B1 through Bi and B1 through Bk is its terminal substring. So, whatever we will be searching would also be initial and terminal substring of B1 through Bi. So, what we notice is that we need not search in this entire space. We can restrict our search to B1 through Bi and look for the largest possible string we can locate, which is initial and terminal. So, what we will do is, if we fail, we would search in the space which is f of I, from 1 through f of I, and again we will try to verify whether the next symbols match, and again if we fail, then we will again search in f of I, and we will continue. If we succeed, then we have got it, otherwise there is no string. So, for that what we will do is the following. Since these may take several iterations, we will have to put this in a loop. So, let us just say, while b j plus 1 is, so here is the final test, we are not succeeding in finding b I plus 1, and if I is still positive, the search strings are gradually shrinking. As long as it is still positive and not succeeding, we will set I to f of I. If we come out of it, there are two possibilities. Either this condition satisfies, or we have shrunk the search space to empty and there is no more to look for something. So, we will then check a condition if the condition would be that if I is 0, then obviously we have not found any string, which would mean f of j plus 1 is 0. Okay. The space was from 1 to I. Let me verify this. The first time, let us just check the first time, this is f I. It turns out for the given I, plus 1 does not match, sorry. So, that may happen that we have nothing here, but the first symbol matches. So, we have to check one more condition, that is, if this is equal and b j plus 1 is not equal to b I plus 1, because maybe the whole string does not match, but the next symbol matches, then we set f of j plus 1 equal to 0. Else f of j plus 1 should be let us see, if I is f j and we find that, so it will be, this is true, so it will be I plus 1. That computes the desired function f, and the complexity of this computation is that in the worst case this loop goes all the way, and it may take at most m steps. certainly less, but no more than m steps. This loop also goes through m times. So, this we can compute in order m square time. Now, we are ready with, we have done some pre-computation and we have enough information to do a more efficient search. What we will do is, we will devise an automaton. A finite state automaton, a finite state automaton in which we will have states from 0, 1 through m, and the interpretation will be the following. If the system is in state j, let us say, we say here a state j if you are currently at state j and you are searching through the text string up to this and you reach, so input will be the text string to this automaton. At the entry of this input, if you are in state j, it would mean that the string b1 through bj, the string, the pattern, initial string of length j of the pattern string matches with the last j symbols of the text. And then we will go to the next symbol. If it turns out to be symbol bj plus 1, then I would like to make a transition from j to j plus 1. So, let us define our transition function delta j and a symbol, let us say we use symbol as p. P is a symbol in the symbol set. This should be j plus 1. If p is same as b j plus 1, we have found matching from b1 to bj here, and if the next symbol comes which is same as symbol at j plus first position, then we have got p equal to the new state to be j plus 1. Now, in case p does not match with the next symbol, namely bj plus 1. So, we have b1 through bj, bj plus 1 and so on. Currently, in our text string we had symbols which were equal to b1 through bj and followed by p. Now, indeed, I am not going to find this matching with this. So, there should be a smaller string I should be looking for which matches with the terminating point at p. So, suppose we have some other location where this goes up to some bk plus 1. In that case, b1 through bk must be, which is already an initial substring of the pattern string, is also a terminal substring of b1 through bj. But we know the longest such string is known to us. So, in that case, we will be looking forward to matching the symbol bk plus 1 with p. If we succeed, then we have found the best string, the longest possible string, initial substring of the pattern, which matches up to this point, and this is of course our text string. these are the symbols matching with the text string. But this problem is exactly the question of where does my automaton jump when it was in state k. Suppose my k is f of j, because that is the longest string which is initial and terminal in B1 through Bj, and I am trying to see after that if P is found, then what is the best string I can find to which matches. So we can directly say that in this case you should go to the same state that you would have gone had you been in state Fj and you had encountered symbol P. Once again, if we compute this from smaller to higher values of j, then this value would have been already known to us, because f of j is strictly smaller than j. So then that gives us a simple algorithm to compute the transition function. So we say d, this depends on the pattern string and the symbol set. For every symbol we have to do this. We will define d0 b1 to be equal to 1. Initially, when there is nothing matching and the first symbol we encounter is b1, then we have found the string of length 1, which is initial and terminal, initial of p and terminal of that length of t. D for all other symbols, p equal to 0 for all p in sigma minus b1. So we have now complete description of the transition function starting from state 0, and then we can put this in a loop for j equal to 1 to m minus 1. Notice that once we reach state m, which means we have found a position where the previous m symbols of the text string match with the first m symbol of p, but p is only m symbols. So we have found a complete matching, and this is where we can stop. So we need to worry about the transitions from these. But in case if you wish to continue and search for all occurrences, you can actually compute this for all the way up to m. And then here you will say if we will capture this if now here we are going to consider for all, for each p in sigma, we are going to have d of j comma p if p is bj plus 1, then that would be, so we will say p equal to j plus 1 if p is bj plus 1, else d of j comma p should be d of fj comma p, d of fj comma p. So, this is just capturing this definition of the function delta. The cost of this computation is, for each value of j we have to scan through each symbol, and the complexity of this is order m times mod of sigma, the set symbol sigma. You have to keep in mind that this cost and the cost of computing function f, which we have used here, is a one time cost. Subsequently, for every text string we can use this transition function. So, this does not have to be computed more than once. Now, let us talk about the automaton. So, here we have the automaton, and we are going to enter the text string. Whenever the system reaches the state m, that should be taken as a terminal state, and we can output the fact that we have successfully found a match for the string p. The cost of computing the transition is unique because we have stored the transition in the array. So, for a symbol p, and if you are currently in state j, you go to this state j prime. Hence, this is a unit cost. So, the entire search will take order n time, be linear in the length of the text string subsequently. It has one drawback, that is, it is dependent on the size of the symbol set. Imagine this is much bigger than m. It is significantly bigger. It is closer to n. That is to say, there are lots of symbols in the text strings which do not occur in the pattern string. In this case, you will end up paying a heavy cost of computing the transition function. In such extreme situation, once again, in case a one time cost such as this is to be paid, we can pay if we have to repeatedly use the same automaton. So, still it is all right. But if you insist that this should be reduced, then there is one trick you can exploit. The trick would be that in the text string, every symbol that does not belong to the symbol set of p. So, any symbol, so this symbol is not in p, this symbol is not in p, and so on. It does not really play any role in the matching. We know that this is as good as a symbol which is alien to p. So, if I replace this by a single symbol, let us say a new symbol, then we can actually still perform the search and we will still get the same answer. The advantage of this substitution would be that the new set sigma, the sigma set would be the symbol set of p, symbol set of p union a special symbol. So, the size of this is nothing but m plus, at less than equal to m plus 1, because at most m symbols can be present in sigma. That can reduce the cost to m times m plus 1, which is order n square, which is also the cost of computing function f. But there is a price to pay for this. You will have to make these substitutions. So, as you are inputting here, somewhere here somebody switches the symbol. If it is found to be alien symbol, not a p symbol, it switches it to that special symbol. What is the cost of doing that? So, in general, if we form a binary search tree storing those m symbols, we run through this and if we do not find it, then we plug in the sharp symbol for it. So, this transition will take log m time. For each symbol to detect whether it is a new a symbol of p or it is an alien symbol. So, in that case the cost will rise to n times log m. This is the price we pay. This will be better than this, because this, if this is huge, this is the order of n, then we are talking about m times n as against log m times n. So, that is the advantage of such a trick. So, we close this discussion and we will discuss another algorithm for the string matching in the next lecture. Okay.